You know Per, he's in the audience. He was the leading brain behind all this. It was done with Dhruv, who was postdoc with Per, and with my good friend Alvaro, who is professor for ages in Sevilla. Now, 1 second. Now, I know, I remember that at this time we should have just finished lunch. So hang on in there for 10 minutes and we are done. The experiment, which is very nice actually. You have a collection of titanium particles of pretty much rough shapes. You put it in a droplet of water with peroxide. For those of you who do not know, titanium with light, it's a photocatalyst and is decomposing the peroxide into water and oxygen. Peroxide is the water for cleaning wounds. And everything is covered in silicone oil. Okay. Now, these particles that I mentioned, which are decomposing a component of the solution when under light, these are the so-called chemically active particles. So they change the composition of the solution around them. What's special about them is that normally by doing this, they start self-propelling in the solution. But now, because the particles actually do have these pretty much random shapes, almost roundish, right? What happens is that even under light, they don't show much of motion. So their motion, if you have no light, it's just Brownian diffusion. If you have the light, it's a little bit of enhanced Brownian diffusion. It just makes longer trips, and then it's still Brownian. You see here in the mean square displacement, this is with no light, this is with light, it's just a little bit of enhanced motion. So you'd say, well, there's nothing special about them, forget about it. Now, this is the part where there is a conflict between me and Windows and whoever did this operating system. Okay, so now you have the drop with many particles and you put it under light. We know that the particles do not move much, as we noticed. And you'd say, well, it's a spherical drop, so it's not going to do much. And you just wait a little bit. And if you wait, and now you see that actually, surprise, surprise, the drop is doing something. Okay? It's an example of self-organization. You notice that the whole thing is moving. Okay? And this was quite interesting. Per was nice and was sharing the results with us. We're trying to actually give I'm sorry?
What is the optical power?
It's very low. It's sufficient to promote the photocard, but it's not enough to warm up the system. This is the worry. I mean, this is if very easily tested experimentally. They just removed the peroxide, kept everything the same, put the laser, and you get nothing. So the particles still absorb, but they don't promote the decomposition. If you don't have peroxide, there's nothing to decompose, right? And you don't get the formation of this pattern. Now, you see this, you say this is example of self-organization, okay? And it's surprising because there's not much to I mean, there is plenty to self-organize, there is not much of a reason to do so. The first question that came to the mind was, maybe there is something, an asymmetry, which is key. Maybe the substrate is not perfect, maybe we have stray fields, maybe there is something to promote a direction for this polarization. And this was very easily ruled out by doing a nice experiment. You turn on the light, you let the pattern to form, maybe you see it, right? You see it in that direction. You turn the light off, you let it relax, you turn it on again, you start again making the pattern, if there was an asymmetry, something, an imperfection, would have been the same direction. But no. Okay, you see the arrows. And you do this, and then again, it will form along a new direction. So this tells you that, well, surprisingly, you have a pure symmetry breaking phenomena. There is a self-organization, really a true one. Okay? Now, once you understand this, then you want to ask questions like, is it really going all the way to zero? So, do I need a certain threshold activity to have this organization? Do I need a certain threshold area of particles to obtain this phenomenon? And you can do the experiments, and again, Per and Dhruv were sort of little geniuses there. I just show you one. This is increasing, or from left to right, there is the decreased areas covered by the particles. And you see that actually the time needed to form this pattern is diverging with decreasing area. We cannot show that it goes to zero. It's zero. Most probably there is a threshold around 3-4%. This is what we learned so far. Okay, returning to the presentation. There were possible reasons for this behavior, and at least most of them could be ruled out. One which was left was, in the end, that actually we do have a brand new phenomena in which you need a couple of ingredients. You need the activity of the particles, you need the induction of Marangoni flows by Marangoni stresses. So you need this particular interface between two liquids, and you need the pinning of the contact line. So you need the confinement to be there. To understand that you really need the Marangoni stresses, that really is new. So it's not the motion of the particle, but the particle inducing stresses, the stresses inducing flow, the flow driving the particles, this changing again the pattern of activity, and so on, till you reach this steady state. To figure out that this is the true reason, there is a simple experiment that one can do, fortunately in this case, by replacing the oil with air. So you still have an interface. The difference is that the oxygen now goes very easily in the air. So there are no longer inhomogeneities and stresses. And if it's so, then you should see nothing forming. And this was actually the case. This was the same drop, but now put in air. Okay, so we waited and waited and waited, and actually nothing has formed. If this was not sufficient to convince everybody, what they tried actually was you change the oil and make different oils with different viscosities. Marangoni stresses are smaller if the viscosity of the outer phase is larger. And that's exactly what you see. The time to form this effect, this phenomena, is actually increasing with the increase of viscosity, and above a certain viscosity simply disappears. So in the right, when you have a very viscous oil, you get nothing, right? So with this, I would like to conclude. This was what I presented. So you have an example of self-organization in a man-made system, and it's brand new because it involves a combination between three factors, which so far has not been reported by anyone else. So thank you very much. This was the talk. Yes.
So can you explain again what was causing the surface tension gradient?
The fact that you release oxygen.
Yeah.
So there is the decomposition of the peroxide into water that's around and oxygen. Oxygen is raising and is hitting the interface.
Okay, so
And
it's
because
only going up.
right, and because the oxygen is produced by the localized sources, and now the sources are no longer uniform.
Okay.
Right, so the sources now are aligned with the particles. When you have more particles, denser, there is more oxygen released there. And this is why the stresses around do have the same structure. You understand? I mean, you have a lot of source in the center where you have this polar and smaller toward the edges. But this is actually self-emerging, and once it's reaching the right arrangement, then it stays.
It's never heard before, like a small molecule of oxygen can change the surface tension.
Well, you'd be I mean, it's not that you'd be surprised. It's because probably you never learned about three-component solutions. So you have the oxygen, which can be in both phases. When you have a three-component and you have water and oil, oxygen can be in both. The distribution of the oxygen, the partition between two phases, this gives rise to a contribution in the surface tension. Okay?
Right, I mean, the experiment's very convincing, but I find it hard to grasp.
Right, but I mean, it's like, then I told you that if the oxygen doesn't stay there, it just goes in the air. So when you have the air, the oxygen just goes in the air. It's very high diffusion constant. So then you have sinks. So not only that we proved that it's a Marangoni flow, but it's actually a proof also that it's a Marangoni flow driven by the oxygen, which we already know. There was the only thing to drive it.
You cannot argue in buoyancy, so the oxygen is going up. But in principle, these are just gas molecules.
If
you diffusing every direction.
If you start
and
with
only an interface between the oil and the.
If you start with the idea of buoyancy,
yeah.
Okay, the buoyancy flows, right, are they should go uniform. So you have a radial flow. We've seen this, right? I mean, you see, if it's buoyancy, then the whole thing would go toward the center. It would be a flow of liquid in the center. You see the radial symmetry, but it's broken, it's not there.
I think it can also happen because it's a drop, isn't it?
That's why I said that actually you need the fact that it's actually peaked.
But you have a gradient because it's a drop.
Yeah, I don't have to take all the time for that.
Yeah. So, with your approval, thank you for your talk. We can discuss further and lunch.